Now in section 11.5, we move away from the controllers and we start moving into generating trajectories. So in this section, we're going to study trajectory messages. The basic idea is we'll have an action server client pair where the action client is going to be providing what we call waypoints, or a series of points along a path for a robot to follow. The server will in turn do some kind of interpolation to approximate the path between points, and then those are passed on to the controllers and the robot. When we have a trajectory generation message, we can either provide a desired angle displacement, in other words, the position, but in more advanced cases, or to provide better performance, we can also include the desired velocity displacement and the desired acceleration. When we do that, the onboard controllers of the robot end up generating some kind of effort that can be joint torques for revolute joints or joint forces for the prismatic joints. And once we have those efforts in the actuator, we're going to get the actual displacement in the motors. One thing we need to be careful about is that when our desired state is far from the actual state, that means our motor will need to have a large change. Sometimes we force the controller to exert an unreasonable effort. That is, it has to work very hard to achieve our desired target. This can lead to the problem of effort saturation. That is, the actuator or the motor cannot provide more effort. It has reached a limit, and so it is unable to actually reach the desired target. If it's not able to reach the desired target, it leads to poor conversions. You cannot follow the points you designed the robot to follow. And when you have poor conversions, then you have unpredictable and dangerous motion. As we study the idea of generating points, we need to separate two concepts. The first one is path planning, and the second one is trajectory generation. With regards to path planning, we're interested in meeting two constraints. The first one is to avoid collisions. So as the end effector of the robot moves in space, we want to make sure that there's never a collision with itself or with the environment. And that whatever path it's going to follow, it never hits any joint limits, or even sometimes gets close to them, because when it does that, we will not be able to follow the desired path. With regards to trajectory generation, we're interested in things like timing. So here we must ensure that our velocities and our efforts don't hit any limits. This way we can always meet our time requirements. So in essence, we're not only defining a path, but we're also defining how quickly we move along that path. Another consideration is that our trajectories should avoid step commands. What is a step command? It's when you provide a big change in your desired target. So sometimes it's like saying we're going to go from 0 to 1. So that may be a large change in your desired path or trajectory. Instead of having these kinds of large changes or step commands, we want to approximate a smooth function as part of this trajectory generation. One way to do that is first set waypoints frequently. In practice, 100 hertz is a good rate at which to set them. Secondly, you want to use smooth functions to approximate the points. Now, ROS is going to help us in the inclusion of waypoints in the system via the trajectory message. So if we do ROS message show trajectory messages join trajectory, we'll see this kind of message. We have a standard header where we can include a timestamp for a specific waypoint and perhaps provide a frame ID for that point. And then we can have an array of joint names. So if your robot has 7 degrees of freedom, each of those joints will have a name. You might call that shoulder 0, shoulder 1, shoulder 2, elbow 0, elbow 1, wrist 0, wrist 1, wrist 2, like that. And for those joint names, we'll have an array of points or joint trajectory points. So these points are, in effect, the waypoints. And because this is an array, they act as a C++ vector or a Python list. So we can generate one point and then append it to our vector. Within the points structure, we have an array of positions, velocities, accelerations, and efforts. All of these work in tandem with the joint names. So if the first element of the array is shoulder 0, then the first element of positions will correspond to shoulder 0. Positions here refer to the joint angle displacement, and velocities refer to the joint velocities, and so forth for acceleration and effort. We also have an element called duration, of type duration or Ross duration, which is the time from the start. So this is what will control the timing for those points. This message works appropriately with just positions, but again, you'll get better performance if you include the right velocities and accelerations that you would like your robot to. So what we're going to be doing now is set the waypoints in the client and then send them over to the action server to generate the trajectory. We're going to specifically look at a minimal one-joint example where we get some coarse samples, points that are not very close to each other. And we're going to generate a sinusoidal curve through the action client. This is a technique we've done a lot for our controllers and for the LiDAR wobbler. So we want to see how well we can do the tracking. Then on the server side, we're going to do a linear interpolation or a piecewise interpolation. So we're going to fit straight lines between the points, which is not ideal, but is just a simple way to represent the example. So we could open these two files in a second. Let me give you an overview of what we're going to be doing here. First, in the client side, we're going to have this goal where we set it as a, now this is Python code, by the way. This is going to be a kind of trajectory action goal. And the type of these messages, of course, is the trajectory messages joint trajectory. We're also, instead of the goal, we'll have the structure with the array. So this will have many points. At the same time, we're going to take single points of the type joint trajectory point, and we're going to assign that point joint name. So for example, if we had two joints here, we could call it shoulder 0 and shoulder 1. And then we have to provide the goal for that waypoint. So that might be, say, 011, 022. And then we need to provide a time at which we want to visit those joints. The way we set those positions must be done intelligently, so there's not the big jump or the big step that we talked about earlier. And then once we have that, we can simply append the generated points into the points structure of the trajectory message. So this is an example. Here we have the name of the joints. We connect the positions in the same order, and then we might create points over time. So a time equals 1, we might visit this location, and a time equals 3, 2 seconds later, visit this location, and then a time equals 5, visit this location. If we ran this example, it would look as follows. Here on the top, we Ross launch the minimal robot description with the minimal robot launch. This is going to start gazebo with a robot in it. This is Arvis, and then this is gazebo right here. We're also interested in starting the action server first. That's from the example trajectory package. And so now it's spinning and waiting. And finally, we start the client and also maybe the RQT plot tool to look at how the robot might be moving. So currently there's no publication of data yet here. Let me fit it on the bottom of this screen for easier viewing. Okay, and so when the client is started, it's going to generate the sinusoidal curve that ranges from 0 to 1. And so you can see that we have this approximate sine curve. And if we start the client once again, you'll see how that joint moves up and down, creating these things. Here you can see the linear segments between points, which seems to be an okay approximation, but we would even desire to have a more smooth representation of the signal compared to that. So here on the client, if we maximize this window, you can see that we are setting points at these time intervals about every 0.5 seconds, and we're providing a sinusoidal curve face that tells where to place the points. Now, this example contains some limitations. For example, it doesn't accept velocities. If we had accepted velocities, this would also provide a better performance. We'll have smoother motions from the robot. And the interpolation, as mentioned earlier, is piecewise linear. Here, it would be better if we used a smooth interpolator like cubic splines. So cubic splines is a technique where you can generate smooth curves across waypoints. There's an example in the Baxter GitHub repository of a trajectory action server that implements cubic splines for the 7 degree of freedom arm and the Baxter robot. And a few more notes is that actually the action server can be designed to have as advanced a functionality as you wish. So you can integrate tools to better control the arm or stop it in place or restart it, or make sure that you don't allow big jumps in the movements of the arm. There's a lot of optimizations that can take place. And please note that path planning is best done on the client side, right? Which points we visit takes place there. It doesn't happen on the interpolation stage, which is the action server. This concludes section 11.5, and moving on to section 6.